part of infrared spectroscopy videos of this series. We're basically going to discuss the instrumentation and handling after seeing all the theoretical aspects in the earlier two videos. In this particular video, we are going to cover the basic aspects of the instrumentation, and we are going to have one more video where we will touch the more complicated and advanced aspects. So when we talk about the instrumentation, what comes in front of us is a basic structure of the IR spectrophotometer with its main components like this is the IR source, and this is the sampling compartment or sampling area, and this is the detector. These are the three integral parts, and finally comes your recorder, which gives you the graph, or which we call as IR spectrum. These are the basic minimum things. Okay, you need an IR radiation source, and then this has to pass through. The sample is to be kept in the path, and after the sample absorbs certain things, whatever is the transmittance is to be detected by the detector, and it has to give the output in the form of a recorder. Fine. Before we go to this thing, let us understand how the IR spectrophotometer evolved. So basically, IR spectrophotometer is mostly used for qualitative determination of absorption or transmission of IR radiation by various organic compounds, and these absorptions or transmissions are characteristic to their functional groups, and the instrument used for this measurement is called as an IR spectrophotometer. Until that, we have three different generations of IR spectrophotometers that have been used. Traditionally, the first generation was in 1950s, which involved prism as an optical splitting system or optical diffraction system. They were made of sodium chloride. They had several limitations, and as a result, now they have become obsolete. The limitations were they're very sensitive to moisture, and I have to be very, very careful using them, because the prism will get affected and it will develop scratches, and its optical properties will get damaged in presence of little bit of moisture. And furthermore, their scan range was very narrow, and the reproducibility of the spectra or the repeatability was fairly poor. And therefore, within a decade, second generation evolved, which involved gratings instead of prisms. These were used as monochromators, and the performance of the second generation IR spectros were much better compared with the prism ones. But they still had several limitations, and they have also been rendered outdated after the invention of the third generation IR spectrophotometer, which are very, very accurate, very reproducible, and very robust. Limitations were, again, they had the same problem of low sensitivity, and they had a low scan speed, and wavelength accuracy was also very low. And so this led to the third generation, which is a modern Fourier transform IR spectrophotometer. These marked the abdication of the monochromators and led to the prosperous use of interferometer. With this replacement, the IR spectrophotometers became exceptionally powerful, and various applications of this are now being realized, which we are going to see. So the main components, before we go into the spectrophotometer itself, first let us study the main components. They are the sources for IR radiations, very different sources. The monochromators, which are the wavelength selectors of the IR radiation. The sampling area or the sample holders, the various types depending on the nature of this sample. The detectors and the recorders. These are the five integral main components of an IR instrument, or that is a spectrophotometer. All modern instruments till today are Fourier transform instruments. All transmission experiments, radiation from a source is detected through the sample to a detector. So all transmission experiments, radiation from a source passes through the sample and then goes to the detector. The measurement of the type and amount of light transmitted by the sample gives about the information about what has been absorbed and vis-a-vis what is the structure of the molecules comprising of that sample. What is very important is ordinary glass absorbs IR strongly, but alkali metal halides are transparent to the IR radiation. Therefore, any material used in IR optic must be made of metal halide salts, particularly alkali metal halide salts. So NaCl is the least expensive of these, but has a limited transmission range. Another replacement is KBr, which is transparent over wider range than NaCl, but is softer and more expensive. Diamond is also transparent to IR, but very expensive. Following notes are to be consulted. Optical cells or plates made from NaCl or KBr are easily damaged if they are mistreated because the crystals are very soft, they scratch easily, and the fog from the moisture in hands causes scratches and rubs on them, and therefore one has to preferably handle them very carefully and preferably use gloves when you handle them. Never touch the surfaces with your fingers because the moisture in the finger or the will create aberrations or smudges on these optics. Preferably store them in a desiccator, so free from moisture. Keep it in a dehydrated atmosphere. Use of an IR drying lamp while preparing a sample is very advisable. When you are preparing a sample and you're going to run a spectrum, you operate under the direct light of an IR drying lamp, which is very advisable. Sources for IR radiation. Following are the different sources, and we have here 5 different sources which we are going to discuss with respect to 6 different parameters. The first one is a nurse glower, second is a glober, third is an incandescent filament, fourth is a mercury arc, and fifth is a tungsten lamp. So these are the 5 different sources. First is with respect to the composition. Nurse glower is made of rare earth oxides, while glober is made of silicon carbide. Incandescent filaments are made of nichrome wire. Mercury arc has, under very high pressure, mercury is filled in it. And tungsten lamp is a tungsten halogen lamp. Operating temperatures for nurse glower are 1200 to 22,000 degree kelvins, and for glober it is 1300 to 1500 degree kelvins. In incandescent filament it is 1100 degree kelvins. Mercury arc is 1000 degree kelvins, and tungsten lamp is 3500 degree kelvins. The radiation produced from nurse glower have much wide range from 4000 centimeter inverse to 12,800, while for glober it is from 400 to 5200, while incandescent filament can go up to 8,000 to 10,800 centimeter inverse. Mercury arc can go below 665 centimeter inverse, while tungsten filament is by far the best and preferred and is up to from 4,000 to 10,100 centimeter inverse. You can take it. So the IR region used is near visible for nurse glower. For this it is middle region. Glober is suitable for middle, while incandescent filament you can go for near infrared if you are going to scan is near. Mercury arc is, needless to say, only far infrared. And see, we are going from left to right in the electromagnetic spectrum, and so on the left hand side will be the higher centimeter inverse, that we call it as near. Above 4000 we call it as near. Something between something between 400 to 4000 we call it as middle, and something lesser than that we call it as far. And tungsten filament is very well suited for 4000 centimeter inverse, so it is middle. Intensity of the radiation is with nurse glower you get the most intense. With mercury arc also you get much intense, but Also with Glober you get much, but with tungsten filament and with incandescent filament you get milder, but they're having longer life. Basically, nurse Glover is used to analyze qualitatively the carbohydrate and protein IR spectrum, and Glober is used for simple functional groups. And, similarly, tungsten is also used for most organic functional groups. Incandescent filament is for complex organic molecules, and for far infrared region mercury arc, which is used, is mainly for inorganic complexes. Now the monochromators or the wavelength selector is the second integral part of an IR spectrophotometer, and these are prisms, gratings and filters. Prisms are made, as I said, either of potassium bromide, sodium chloride or cesium iodide, and these are the prisms particularly. Mostly they are made of KBr or NaCl. Cesium better quality, of course. Diffraction gratings are another type of monochromators. We can say the second generation. Again, they are made of potassium bromide or sodium chloride, and these are such type of gratings where the white light is getting dispersed, and these are again made of this dispersed light is again passes through the holographic gratings again to give you the monochromatic light. Filters are made of lithium fluoride. These are the filters like the SLR cameras where you change the filters. These are also the filters, and particularly this is the filter cap, and here this is made of lithium fluoride. This fits inside and it filters only particular radiation and allows it to go, others it stops. Sample handling techniques are very important, and we are going to see these sample handling techniques. Let us see these sample handling techniques. Solids are actually generally we use the press pellet techniques, that is sample plus KBr in a proportion of say 1 crystal to 100 crystals. These are filled in a stainless steel die, like a tablet die, and it is also fitted with a punch, and so this is put in the die hole, and then the punch is fitted, and then over it is applied a very huge hydraulic pressure of 25,000 psi per gram, and that pellet is formed, which is a transparent, thin, very thin, you can say pill or tablet type of as almost you feel like a glass pellet, very thin. Second is a mull technique, which is a suspension type of solid and an oil liquid suspension, where you use the liquid which is used, which is IR transparent, which is either liquid paraffin or a newsol or a hexachlorobutadiene, and this is preferably dried over sodium wire or molecular sieves. Solid run in solutions, no water and alcohol, but solids can be dissolved in carbon tetrachloride, carbon disulfide, chloroform, which are extremely dried again, and these solutions can be sprayed on the sample holder as thin films. Between two sample plates, they can be a drop or two can be poured, and the other sample plate is fitted over that, and so it forms a thin film. In solid films, if a solid is amorphous in nature, the sample is deposited on the surface of KBr or NaCl cell by evaporation of a solution of the solid. So this is another technique. You can take this solid solution in carbon sulfide or carbon dichloromethane, which are somewhere having a boiling point of 45 to 42. You can mix it with this KBr, and then you can put it in a rotavap or something, and you can suck out the solvent. So the solid is uniformly distributed over the KBR, and this can directly be forming a fill over the KBR, and this can be directly used in something like a sampling system of ATR. How liquids are done? Liquids are usually handled pure, since all solvents have their own absorption spectra. Highly viscous liquids are analyzed as thin films squeezed between two NaCl IR transparent plates. The same thing I told you, solutions also are squeezed between the two plates, so they form a thin film. Just put a couple of drops and squeeze them. Film thickness is so thin, 0.01 to 0.1 mm. For samples that contain water, plates are constructed with calcium fluoride, which is resistant little bit. Gases and low boiling liquids, no prior and special preparation is needed for spectra of gaseous samples. 10 centimeter long cell is used to run these samples. In order to reduce the length of cell, several baffles, that is reflecting surfaces, can be introduced. Thermally stable metal transition complexes are usually measured in gas phase. Now let us see the experimental how to do the sampling. To obtain an IR spectrum, the sample must be placed in a container or a cell, which is called as a sample holder, and that itself should be transparent in the IR region of the spectrum. Sodium chloride or salt plates are common means of placing the sample in the light beam of the instrument. These plates are made of salt and must be stored in a water-free environment, such as the desiccator shown here. So these two, you can see, these are the sample plates made of NaCl or KBR, and this is the sample holder. So this plate will fit here, another plate will fit here, and over this you can, through these holes will pass through this, and this will be again tightened with screws. So these are IR transparent salt plates, and this entire thing, these screws I told you, this can be bolted. This ring can be bolted over these plates to hold them in place, and this entire thing can be actually kept in a desiccator, which is having silica or calcium chloride or any dehydrating agent, magnesium oxide or something like that, anhydrous. Let us continue with the experimental. The plates must also be handled with gloves to avoid contact with the plate with moisture from one's hands. Fine, they should be handled with gloves. To run an IR spectrum of a liquid sample, a drop or two of the liquid sample is applied to a salt plate, and a second salt plate is placed on the top of the first one, such that the liquid forms a thin film sandwiched between the two plates, and then this is put, as I told you, and this is bolted. The cell holder is then placed in the beam of the instrument or the radiation path. The sample is then scanned by the instrument utilizing predestined parameters. A satisfactory spectrum has well-defined peaks but not so intense as to cause flattening on the bottom of the peaks. So this is then put inside. These are the plates. In between the film is formed, and this is fitted nicely in this, and from here the radiation comes. This is the standard and this is a sample, and this keeps on moving in the path alternatively. Fine. The salt plates are cleaned by rinsing into a waste container with a suitable organic solvent, commonly cyclohexane. Never use water. Cloudy plates must be polished to return them to a transparent condition. To polish cloudy windows, rotate salt plate on a specially supplied a polishing cloth which is very soft. Okay, fine. They should be washed with cyclohexane and then they should be polished. How to prepare a KBR disc? So this is KBR and these are the sample crystals. Fine. And we are compressing this, so finally we are getting a disc. So this is a die. This is a punch. This is a die. This entire thing is a die. This is a punch. Here is a upper anvil. Here you put the sample. This is the lower anvil in between, and then this is a hydraulic plunger which exerts very huge pressure. This looks something like this. Yeah, there is a manometer to measure it, and here you get a pellet, and this is triturated in agate and pestle and agate using, and these are the this is the monkey spanner, and this is the handle of this plunger. So maneuver, these are used to maneuver this. Sometimes you use mulls for solids instead of making pellets, so that are not soluble in transparent solvents and cannot be conveniently pelleted in KBR. They are taken in form of suspensions, and which are obtained by dispersing the sample in a mineral oil or a fluorinated hydrocarbon in form of a mull or a suspension. So this is a pestle agate made of a special material which is very tough, and a few drops of nugol and the solid, and a mull is made. Grinding 2 to 5 milligram of the finely powdered sample in presence of 1 or 2 drops of heavy hydrocarbon oil like sodium dried liquid, paraffin or nugol. By grinding this, if the hydrocarbon bands are interfering, then use a halogenated polymer called as fluorolube, which is little bit costlier. Resulting mull is then examined as a film between flat salt plates. So this mull is put here, again this plate is put here, and then this is these two are put inside, and then this plate is bolted over here, and then this entire sample holder is fit in the path. So in the mull technique, a small quantity of sample is thoroughly ground in a clean mortar until the powder is fine. First make the powder fine, and then you add a few drops of the mineral oil or nugol, so you get a consistency of a toothpaste. This is then transferred to the mull plates, and the plates are then squeezed together to adjust the thickness of the sample film, and this is mounted in the path of the IR beam, and then the spectrum is recorded. You have a latest technique which is called as ATR, attenuated total reflectance cell, which is made of a diamond surface, and you require just sample. You don't need to make a KBR pellet or a solution or a mull. Nothing is required. Just place the sample, few crystals pressed into the diamond surface here. Okay, just place it. At the interference of the diamond surface, the incident IR beam transmitted at an oblique angle. Okay, and this is the incident beam, and it is transmitted at an oblique angle to the sample is changed, and at the oblique angle penetrates the sample, and due to this some of the IR radiation is absorbed by the sample, and this is again refracted, and of course the transmittance is low because some has been absorbed. Well, ATR is faster and more convenient. Higher quality spectra are usually obtained by KBR disk only. KBR disk is the most preferred method of sampling. When you use ATR, you have to be certain that the cell is clean, otherwise you may get an IR of another person's sample. So what happens is, because this is such a simple technique, just put the sample and put this diamond on the surface of the diamond, what you can say, surface, and then put the anvil and just pass this thing. No, but what happens is actually people forget to clean it thoroughly. Just wiping it will not help. You have to clean it with some cyclohexane or something, and then ensure it is totally wiped off properly. Otherwise, the earlier sample will also add to some peaks, because these are very, very sensitive instruments. So here you put it here. This is a sample, and this is ATR crystal, and from in between this goes from this thin slit, and incident radiation was much more. Sample is absorbed, so some percentage is transmitted. What are the detectors or transducers, which are of three main categories: thermal, pyroelectric, photoconducting. And more important for us are the thermal, which are the bolometer, thermocouple, thermistor, and Gole cells. And under this, we are going to see more in details four types of detectors: thermocouple or thermopile, thermistor or bolometer, pyroelectric, and Gole or pneumatic. And however, pyroelectric are more useful from FTIR point of view. So first principle is the Pelletier effect for thermocouple, Wheatstone bridge for thermistor or bolometer, electric polarization for pyroelectric, and for Gole or pneumatic it is the expansion of gases. Materials are also given for thermocouple. It is either bismuth and antimony coated by metal oxides. The thermistor is sintered oxides of manganese or cobalt or nickel. And pyroelectric are made of TGS, that is triglycine sulfate or lithium tantalate. And Gole are generally made of xenon. Material should be thermally active for thermocouple or thermopile, thermally sensitive resistors for thermistors, and non-center symmetric crystal for pyroelectric, and inert in nature for Gole or pneumatic. Xenon itself is also inert. Description: the half junction hot, alternate junction is cold. So alternate junction is hot and cold, while in case of Gole it is a metal cylinder closed and built on the metal plate and silver. Conversion in it, radiant to electric signal is measured, change in resistance. And in case of pyroelectric it is thermal alteration to electrical polarization, and in case of Gole it is expansion of gas to pressure leading to E signal, electrical signal. These are used for photocaustic spectroscopy, thermocouple or thermopile. This is thermistor or bolometer is used for diffusive reflectance, and pyroelectric is used for FTIR, and Gole or pneumatic is used for non-dispersive IR. Response time is 60 seconds, for thermistor is 4 seconds, and pyroelectric is very fast, multiple scanning. Gole is also very fast, 0.01 second. So now coming to the IR spectrophotometers, there are two types of IR spectrophotometers. First are the first and second generation dispersive IR spectrometers using prisms or gratings to spread the spectrum of incident radiation to the detector. Well, the FT-IR spectrophotometer collect all wavelengths of IR simultaneously and use a beam splitter which is in the interferometer. And so FTIR does not use any slit to limit the individual frequency reaching the sample and detector, while the dispersive uses narrow slits to select one after another type of frequency, and so they are slower. This means the signal to noise ratio of an IR spectrum measured by an FTIR is much higher because it takes the entire radiation, and that is attained by much higher than that is attained by the dispersive type of IR instrument because it takes one by one. So let us see. This is a typical dispersive IR spectrophotometer. You have got an IR source, and this is a splitter. It divides the radiation into two parts, and one goes to the sampling cabinet, one goes to the reference, and then there is a splitter chopper mirror which alternatively sends the sample and the reference standard radiations through the monochromator, which has a series of mirrors and gratings, and then it sends it to the IR detector. So a double beam design with two equivalent beams from the same source passing through the sample and reference chambers as independent beams for analytical comparison of transmitted photon wavefront information. So you got a reference, you got a sample. An optical chopper such as a sector mirror focuses this reference and sample beams alternatively on the detector. And the emitted wavefront of the radiation is dispersed by a monochromator, a combination of prisms and gratings of variable slit mechanisms, and this is the monochromator. Narrower slits better resolution by distinguishing more closely spaced frequency of radiations, while wider slits more light to reach the detector and provide better system sensitivity. So you should have a combination of narrow and broader. Very narrow, then light may not be that much. Very broad, you will have less selectivity. The emitted wavefront beam, that is analog spectral output, hits the detector and generates an electric signal as a response, and this is the detector. So finally this is emitted out to the IR detector, and then the detector has analog to digital, and then it goes to the recorder and all things. We will see much simpler view of again the dispersive type of IR spectrophotometer, and we will try to nicely explain it. A block diagram of a classic dispersive IR spectrophotometer. So this is from the IR source, this is the incident radiation, and this has diverted to the sample, and another divergent it is a splitter. It has splitted it in two equal parts, one going to the sample, one going to the reference. Again, the reflected mirrors are further guiding them to the sample and reference compartment. Now it passes through the reference. A reference is quite transparent, so it remains of the same intensity. However, when it passes through the sample, a little bit has been absorbed, so it changes. Less is transmitted. Again, these are reflected through some mirrors, and then they again go back to another system of chopper or splitter, and this again sends them to the splitter. The splitter then combines them. So detectors are the devices. Now it sends to the detector that convert the analog spectral output into an electrical signal, and are further processed by the computer, that is the processor, using mathematical algorithm to arrive at the final printout of the spectrum. These are the detectors. So A combination of this is now different. It is sent to the detector. From via detector it has gone. It is absorption of IR radiation by the sample, producing a change in the IR radiation intensity, which gets detected as an off-null signal different from the reference signal. Each frequency that passes through the sample is measured individually by the detector, which consequently slows the process of scanning the entire IR region. And recorder, the change is translated into recorder response to the actions of synchronous motors, resulting in a spectrum printout. So recorder is a processor, and it is converting this into an output, a graphic output. So it is converting it into a graphical output. So analog to digital, you get such a spectrum. So basically this is how traditional dispersive IR spectrophotometer works. And friends, we will stop here because we are going to now next video we are going to see the FTIR, the concept as well as the phenomena of FTIR.